Cool. So what I'll be covering here is what the app container spec is, which is a specification that we helped initially write along with some other folks around how to build a app container image and how that container image actually gets executed, and then a implementation of that spec that we built called Rocket. So I'm Brandon Phillips. I'm the CTO and co-founder of Coreos. You can find me on GitHub and Twitter if you'd like. So the title of this talk, which I found out about 2 days ago, is Rocket and the Need for the App Container Specification. So let's start with what the need is here. So CoreOS doesn't ship with a traditional package manager like RPM or Debian. And really, containers bring up this question of what does a Linux distro mean if you have containers, if all the applications are shipped in containers. And so the reason this becomes a question is because if we have containers, this is traditionally how the Linux distro is kind of partitioned. We have this all this stuff in green that is shipped by our distro, and then we have this thing in white, usually some Java code or some Python code or some Ruby code that we kind of place on top. And so our distro kind of provides all those user-level dependencies. But things kind of get switched around and broken a little bit because you start to depend on very little of the things that are shipped in your distro with containers. And so really with containers and how we originally thought about this stuff is that it's Linux packages 2.0. And so what we would like is essentially a deb or an RPM for containers. So what are the properties of the package managers that we've relied on for nearly 25 years in the Linux ecosystem? What makes a package manager? So there's some bad things. There's package collisions, right? We have local namespace collisions like, I have this Python installed, and then I need to run this script that requires Python 3. Bad things will happen, and we have all these kind of hacks around it. We have update alternatives, et cetera. And similarly, we kind of have the inverse thing. My app needs this new thing because we hired an intern and he was really excited about using Python 3 in this application. And now some of our Python 2 stuff stopped working on this particular server. So this is not so great. And we've kind of worked around it in various manners. But it's kind of a binary decision that we have to make. Dependency namespacing. Who here has ever been in a very desperate situation where you're just missing that one piece of software on your server, and you're like, I'll just go to rpmfind.net, and this will work out? Has anyone thought that, seriously given that consideration, you're like up 2 in the morning, you're like, I just need this one RPM, it'll be fine. So you find something that looks right on RPM find, and you're like, well, it's from SUSE, so I'm sure this will be just fine on my Fedora box. Well, it turns out everything's not fine, and you will be up until the wee hours of the morning. And so this dependency namespacing where the distro essentially is very authoritative and says, hey, the name of glibc is owned by me, and I'm going to break it out how I want it. I want to version it how I want it. And it means we can't kind of just swap in and out different chunks of software onto our hosts. But there are a lot of good things about the package managers, a lot of things that they got correct. So we have the idea of a user-controlled trust. So your distro ships with some default, essentially GPG public keys that you trust. And when you do your apt-get update and your apt-get install, these are the keys that verify those packages that you download from the internet. Very good. We have really trivial mirroring. So it's easy for us. We know that we have 10,000 servers inside of our data center. It's easy for us to have a single cached copy of all the distro software that we need. And it's trivial to host those on an NFS mount or to host them on an HTTP server. This is really fantastic mirroring. Gives us this property that we can kind of do access control around our network. We have really hot caches inside our data centers, and we're not wasting that precious outbound internet. And we also have this proliferation of tooling. So we have these sort of adapters all over the place. The Debian ecosystem has really fantastic tooling. So I can take something like a Python package and say py to DSC, which is the Debian source, like the .deb source format, and it generates me a Debian package. Or there's there's this great tool. How many of you have used effing package manager? Okay, this is fantastic. It essentially it's when you throw up your hands at whatever build tools your distro has and says, I just want this Ruby script or this Python script in an RPM or a deb. And so this thing understands the specifications of RPM deb, packages in, throws in whatever files you want, and just actually makes it a deb or RPM package. And then there's things that convert from deb to RPM. I have no idea why people continue maintaining this tool. It's worked for me like 0 out of 10 times, but the idea is there, right? So the app container spec is an attempt to take the good that we see in these package management systems, this idea of tooling proliferation, this idea of trust, this idea of a completely shared and non-conflicting namespace, and make that a standard for containerize. And it's an open source project on GitHub, github.com/appc. The primary repo is the spec, which is /spec, and then there's a discussion mailing list. But nearly all the discussion happens on the pull requests around the spec and the issues around the spec. Right. So it's an open specification for running applications and containers. And I want to be very specific. The reason we called it the app container spec is because there are kind of specs around what does a system level container look like? What does a container look like that executes a real Asp in a init, is a full root file system in and of itself. And this is particularly about running application containers, which is I want to run this Redis process, and I want to run this web server process. So it's just the application container. And it's important to note that app container is not Rocket. We don't call these files .rocket files. They are app container images. And kind of the reason I think this is important, the rest of us think this is important, is because we want to see lots of implementations of this spec. And also, it's so difficult sometimes to explain to people, wait, I'm running Ubuntu and I'm installing a Debian package. Is this correct? So let's just avoid it straight out and just call it a separate thing, completely neutral, the app container image. All right. So containers, we all understand. Otherwise, who doesn't understand what a container is? Okay. They're isolated, self-contained little bits of binaries. You can ask the guy next to you, the person next to you, if you want more information. So why did we build this? Why is there a need for this? We wanted to have an independent group, independent specification, independent of any implementation. And we've taken contributions from Cloud Foundry, Mesosphere, Google and Red Hat engineers on these teams, and many others. We have a governance policy. We want to bring on maintainers as more implementations of the specification pop up. There's a handful that I'll cover in a moment. And so we want to just talk about the spec. And it's really easy to keep a community focused on a particular thing if that's the only thing that exists. So just the spec, very little code. We wanted something that was very, very simple to understand and implement. But we wanted to make sure that we took advantage of optimizations where possible. So for example, we designed for having content addressable storage so that people can cache these things. We wanted to have the ability to separate out layers and have dependencies so that you can have a single image that depends on 2 or 3 other things so that you get that caching ability and that reuse of the actual binaries, even if the configuration of how you run those binaries change, whether like the environment or command line args or whatever, you don't have to ship around additional bits just for those things. We want it to be secure with cryptographic image addressing. So the primary identifier of all app container images is the SHA-512 hash that's been shortened to 256. And then image signing and encryption. Signing is in the spec and is a GPG-based signing mechanism. Encryption is currently being discussed. And we wanted to use essentially the world's most boring tools possible. tar, gzip, GPG, HTTP, and then leave room for extensibility for things like transports over BitTorrent or compression through new compression algorithms. And there's a bunch of interesting work here using these really boring tools. is good in that lots of tools can build these things. It's bad in that the tar format, I think, is probably one of the craziest binary file formats I've seen. And it's nobody's fault. It's just when you start to think through, I want it to be backwards compatible with this piece of software that was written in the 1980s, and you tack on the requirements of 2015, you have a large range of things that you need to keep in mind. And so we have a bunch of interesting things built on top of tar and gzip that we'd like to do in the future. You can do things like address and stream these things, even though they are kind of these complex binary blobs. And then we wanted for the spec to be composable so that it can be integrated into existing systems that may not have had containerization, or existing systems like your existing init systems. And we wanted to be non-prescriptive about workflows. That's why we talk about the spec and what actually that app container image looks like, not how you build the app container image. And then we're completely OS and architecture agnostic. So there's already a port of the app container spec to ZFS and FreeBSD as an example. And so we want the spec to be about how do I ship bits, and then how do I run those bits on an operating system, not necessarily what that operating system is. So there's a number of components to make this whole thing work. Obviously, there's the image format, which essentially is a root file system plus a JSON manifest. And as I said, it's uniquely identified by this cryptographic hash. There's image discovery, which is how do I take a name? So one of the core tenets that we initially established is we wanted to have a shared namespace that didn't collide. And so the discovery mechanism relies on the DNS namespace. So I can say I would like to run coreos.com/etcd. And what happens is it goes off and makes an HTTPS request, looks for some metadata in the URL body that it gets back, and it finds out where to actually download the app container image from. In the case of coreos.com/etcd, the hosting is provided by GitHub. Thank you, GitHub. And we host about 40 bytes of metadata in our HTML website on coreos.com. So we do all the glamorous work, and GitHub does all the hard work of actually storing those bits. And then the container spec talks about how the actual image is executed. The idea of a group of applications, which was talked about in the previous talk, this idea of a pod, how the actual container is executed, what does that runtime environment look like, how is the container isolated from the rest of the system. And these are both generic mechanisms, like using various POSIX constraints, like R limits, or using OS-specific constraints, like C groups on top of Linux, and then how the networking is set up. In the case of Rocket, we have various numbers of various ways of setting up networking. The primary two ways of being private networking, where you get an IP address assigned to this container or this pod, and host networking, where that container actually runs in the same network namespace, has access to all your Ethernet devices. And then the last bit, which is a little bit more, I would say it's a harder problem for people to get their head wrapped around, is the idea of a metadata service for containers. And in a similar way that today our servers have an identity, so our servers have this identity of an SSH host key, which is generally, for better or for worse, is generated on first boot. And then we SSH in and we type, yes, I trust that. And then you hope you never have to think about that, what you just did, ever again. But this idea of a piece of compute having an identity isn't something that we've kind of tackled with containers yet. And so the metadata service provides a cryptographic identity to the actual running process in a similar way that there's a cryptographic identity for our running servers. And there's a cryptographic identity that we give to ourselves, our SSH keys. So this one's a little bit more abstract, but it is something that I think is an important idea that we should try to tackle as a community of people trying to implement these technologies. Because for the first time, we kind of have the opportunity to shove in identity into the process. So there's there's a number of community projects out there that I mentioned. There's a C++ implementation of the app container spec. There's an actual C++ executor built for Linux. Mesos has some work in progress stuff to host or to directly download and execute app containers inside of Mesos. This is the FreeBSD ZFS implementation called Jetpack of the app container spec. And then we have a number of build tools, this idea that we want to have lots of build tools. ACI do is interesting in that it runs and builds an ACI inside of a running ACI container. We have a Docker to ACI tool to convert a Docker registry image to a ACI that you then can sign and then host up on an HTTPS URL. Go ACI, which the basic user experience there is I type Go ACI and then a Go package, and it pops out a statically linked Go binary that's wrapped inside of an ACI metadata so that you can directly run that sort of stuff. And so the basic status of the app container spec is that it's rapidly stabilizing, and we want to get towards an initial 1.0 as quickly as possible because, as you can imagine, as you add a proliferation of tooling, you certainly want to make fewer and fewer backwards incompatible changes. So, I mean, imagine if somebody did something crazy like, make HTTP a non-text protocol. It'd take forever for that to roll out. Well, HTTP2 is primarily a binary protocol. Anyways, all right. So let's talk about Rocket. Rocket is a implementation of the app container spec. It's the one that we built at Coreos. It again is on GitHub and has a development mailing list. And it does the discovery piece, which is how do I take this name, coreos.com/etcd, and actually find that binary, download it, and then and verify it. It executes that thing once it's been downloaded and verified and unpacked, and then implements the metadata service that we talked about for giving identity. It is Linux specific. It's very unlikely that we'll port Rocket somewhere else unless somebody comes along and does all the hard work for us and rebases it. And then it's completely self-contained, so we try to be completely isolated from the host as much as possible. So it should be a single static binary that you can run on top of any Linux distribution. So a binary release that you download off of GitHub of Rocket should be able to run on its own on top of Debian or Fedora or whatever distro of choice you have. And it's completely init system agnostic. A lot of people have the idea that it's specific to systemd, but it's not. It runs under Upstart or sys5 if you're using that or anything like that. And an important property of Rocket is that it's a command line tool only. There is no long-running daemon required for running a Rocket process. And apps run directly underneath the spawning process. So if I run Rocket under bash and my bash goes away, it's going to die. And you can run it under any regular process monitoring system. Okay, so taking the whole Rocket theme, we have a modular set of discrete stages that happen inside of a Rocket execution. So we have stage 0, which is where all a majority of the Go code is. And that is the downloading, discovery, unpacking, setting up of file systems. And so that stage 0 essentially gets us to the point where we're ready to start executing something. And a stage 1 is packaged as an ACI itself. The idea there being that we ship an ACI, a stage 1 ACI with Rocket, that is systemd inside of an ACI. But people have prototyped out like a KVM ACI or a NoVM ACI too. So the idea that we decouple the downloading of and verification and file system setup from how the container actually gets executed. If people want to have a different thought on that, or if they want to use a different init system or whatever. And that API is slightly unstable at the moment, but it's something that we're trying to get to stabilization so that we can kind of swap out these stage 1s in a given release of Rocket. And its primary responsibilities are essentially everything that a init system would be responsible for. So executing the actual application, process monitoring, and then setting up of the C groups, et cetera. And then stage 2 is the actual app that you want to have executed. So in this example that I've been using so far, it's the idea of that I'll be running user bin etcd or whatever is in that ACI. And then there's a number of subcommands that are used with Rocket. So you fetch something over the internet, you run that thing over the internet, and you address it by either a direct HTTPS URL, a discovery name, so like Coreos.com/etcd, or a hash. You run those things, which actually starts the process. And then we have the usual tools that you'd expect. So you can enter a running pod or container. You can list all the running pods or containers. And these sorts of things are implemented by using POSIX locks in a well-defined directory structure. So we essentially have a directory of all the containers, and we walk those things. And we're able to figure out the status and do garbage collection based on whether the process that was launched is dead or not. And so garbage collection is actually sort of an interesting one because it's not actually a long-running daemon. You could put it on cron or as a timer or run it periodically to garbage collect containers that have exited. And there's policies around whether you want it to be a time-based garbage collection, et cetera. A very important one is Rocket Trust, which lets you put in a URL, say Coreos.com, and say I trust whatever the HTTPS URL on Coreos.com publishes as their ACI signing key. It does a little confirmation workflow where you can confirm the fingerprint if you'd like, and then it gets stored into /etc Rocket. Yep, I already covered this, the idea that the ACI, the stage 1 is actually an ACI itself. And also, Rocket strives to have Docker image support also. So you're able to do things like download something from the Docker index of, say, Redis with the tag of latest. All right. So who saw the launch yesterday, or the landing? Yeah? I'm going to do a live demo with a bunch of code that I wrote on the train over here. So I'm sure this will go just fine. All right, let's get the terminal up. Okay, so let me get to the. So what I'm going to do really quick, I have about 3 minutes. So what we're going to do is walk through how to take a statically compiled Go binary, turn it into an ACI, and then get that ACI running under Rocket on a host. Okay, so I have this program that I wrote this morning. The idea here with this program is it does two things. It has a health endpoint that returns 200 and an OK in the body, and then it listens on port 5000. And then the program also watches and backs up an etcd write-ahead log directory. So it just sits there every second and copies the files from the current data directory of an etcd process and copies them to a backup directory. I was going to be really cute, and I started down the road of having this backup to S3 or Google Storage, but then I realized every time I've done something over the internet with at a conference, it's always failed because Wi-Fi. So I got much less adorable. So the first thing that we have to do here is we have to actually statically compile our binary. So this long command line essentially tells Go cross-compile the Linux from my laptop, which is running Darwin OS X kernel. And so what we should get out of this is an etcd backup binary. That's an ELF64 binary. Fantastic. Then we have a manifest that actually describes this. This is the app container manifest, essentially saying that, of course, this code is 1.0. It's running on an AMD 64 processor. It's designed for Linux. It's going to expose a health port on TCP 5000, and then the two mount points, which are the data dir and the backup dir. Great. So the next thing we do is we run AC tool. So we copy the binary that we just built, so the etcd backup binary. What? All right, going back to my instructions. So we copy the manifest and the binary into the, where'd my cursor go? Okay. So we copy the manifest, that JSON manifest, into this directory layout that we're going to use as our template. And then we're going to copy the actual binary itself into the bin directory of that template. Okay. And then we use the AC tool, which is a generic Swiss Army knife for dealing with app container images. And this will take this flat directory layout and actually build the ACI. So it'll tar it up and gzip it and validate that the manifest that we wrote is correct. Oops. OK, cool. So now we should be able to do AC tool validate the etcd backup thing. It returned without an error code, which is not very helpful. Valid app container image. Fantastic. OK. So the next piece is we'd actually like to sign that. So I'm going to skip over actually generating the RSA key. And what actually has to happen here is that we use our GPG RSA key that we just generated and actually sign the payload and generate an ASC. And don't tell anyone, but the passphrase is rocket. I'm going to override the last one that I built. All right. And so at this point, we should have a valid ACI and a valid ASC that actually signs that. So we'll scopy these things over to a VM that I have running on my laptop. Uh-oh. Where'd the ASC go? Uh-oh. This is bad. Oh, I see what I did. OK, so we have an ACI and an ASC. We'll go over to the host. This is just a Fedora machine, I think. Yeah, it's a Fedora machine that has Rocket installed. And so what we'll do is we'll run this etcd backup tool, this ACI that I just built, and etcd together. And what should happen is that we'll have etcd running, and then periodically that WAL file will be copied over. And these two things will run together in a pod. So these processes will live and die together. So we'll do rocket run. And there's a few details here that you need to see. First is that we define a volume, which is our data dir. It's a kind host. So Rocket has various types of volumes that it can mount. And it'll be at temp etcd. And the other one will be the backup dir, which is where the backup tool will actually copy copy into. And then I have offline copies of etcd and the backup thing. So what should happen here is that signature verification passes on both of those because I already have the GPG key in my etc RKT. And you'll see here that the process is telling me every second that it's successfully backed up the WAL file. And so proof is in if there's actually data here in etcd backup. All right. What are the chances? Woohoo! So to go even further, what we should do is set a key in etcd. We'll set the key foobar to it worked. OK, so that successfully got written into the etcd cluster. Now, if I run strings over it, I tested this with container.camp, but let's see if it works with it worked. Woohoo! So we have this idea now of we have an atomic unit of multiple processes running together, and you kind of want these things to be separate abstract ideas, this idea of a backup tool and a database tool. And they run together as a single process. And that is my Rocket demo. And I think I'm over time. So it worked. Thanks, guys.
Thank you, Brandon.